Well, hello everyone, and welcome to today's webinar entitled Drones, Camera, Droplets, and More, the latest technologies for crop sprays. I'm Chris Boomsma, Director of Education here at the American Society of Agronomy. It's my privilege to be the moderator today and to bring another Crop Protection Network sponsored webinar to you. Webinar number 5 in this series, so it's fantastic to be back, and we're going to get started now. So as I said, this series is sponsored by the Crop Protection Network. Do note, though, that sponsorship of this webinar does not imply endorsement of the sponsor's views, products, technologies, and/or procedures by the American Society of Agronomy. But we do thank the Crop Protection Network bringing a lot of quality education in the whole pest management space. So with that, let's go over some housekeeping items as we usually do. First of all, if you are having any issues with some aspect of this webinar, please contact first my colleague Lacey Edwardson. You can see her email address and phone number on the screen at this time. If you are having trouble viewing this webinar, you can reach out to her at 608-268-4953. Again, 608-268-4953. Note that this webinar is worth 1 CEU in precision agriculture or professional meetings, depending on your certification. We will have a question and answer period at the end of this webinar, as we always do with our webinars. And so please submit your questions at any time. I will take those questions and then pose them to our presenters during the last 5 to 10 minutes of this webinar. Note that this training session is being recorded. You will have access to both the recordings and the slides shortly after this event. And I can say pretty much for sure within 1 week, but we try to get it to you in a couple of days. So be on the lookout for that. Next, be on the lookout too for future webinars offered by the American Society of Agronomy, including more webinars associated with this particular series. For more information about this series, you can go to the address on your screen, agronomy.org/education/online courses/crop protection network. You can see that there. Just type that on in, and you'll see the other remaining webinars in the series. Okay, so that's all for housekeeping items today, and now over to our speakers, and I'm going to introduce both of these folks to you. First of all, we have Dan Martin, who is a research engineer with the United States Department of Agriculture, Agriculture Research Service, or USDA-ARS. In this role, he focuses on developing and implementing aerial methods for spraying crops, and is currently investigating the use of spray drones in precision ag applications. Prior to working at the USDA-ARS, he directed the Aerial Application Extension Program for Louisiana State University, or LSU. He has a bachelor's in ag engineering from Virginia Tech, and a master's in biological and ag engineering, and a PhD in engineering science from Louisiana State University. Dan, thank you for joining with us today. It's a privilege to have you as a speaker. Now, to our second individual who will be joining us, and that is Tom Wolf. Tom is the owner of Agrimetrix Research and Training located in Saskatoon, Saskatchewan. His team principally focuses on improving spray operation efficiency. He also jointly runs an educational website for spray practitioners called sprayers101.com. Before launching Agrimetrix, Tom was a research scientist with Agriculture and Agri-Food Canada. He's an active member of the Canadian Wheat Science Society, where he has served on the board of directors and as president. He has a bachelor's in agriculture plant science and a master's in plant science from the University of Manitoba, and a PhD in agronomy from the Ohio State University. So welcome to you too as well, Tom. All right, well, we're going to get started with this presentation. Again, thanks everyone for joining us today, and I am now going to hand it over to our first speaker, Dan, who is going to talk the first part of today's webinar. And when you're ready, you just go right ahead. We look forward to your presentation today.
All right, thank you, Chris. Appreciate that. So let me get myself out of the way here. Hopefully I can do this without, oh, there we go, good. So as Chris said, my name is Dan Martin. I'm a research engineer with USDA in College Station, Texas, and I'm going to talk to you a little bit about 2 different topics, really. One is the first will be challenges and opportunities for spray drones in agriculture, and then I'm going to present some efficacy work that I did this last summer for control of rice sheath blight in Louisiana. So the first part of it is dealing with spray drones, and in the U.S., drones have become more popular and more available and more affordable over the last 4 or 5 years for doing spray applications. They've been used for remote sensing for many years now, actually, and have been used for spray applications in Asia, East Asia, for over a decade. But just only recently in the U.S. have they become available and affordable and commercially viable tools to make spray applications for crops. So you may be familiar with drones such as this that you can find off the shelf. And these are great little drones that have a very portable, inexpensive. They have a camera. They can be used for agriculture, for remote sensing, and for surveying houses and rooftops and those types of things. Or you may think of a drone as the military type version, as the Predator. But what we're really talking about today is going to be spray drones. And with the spray drones, these drones have all the systems that you would find on a manned aerial application system. They have a tank, like a hopper right here. They have pumps underneath the aircraft right here. They have booms out on the left and right side on this one. And then they have nozzles. So on this one, we have 2 nozzles on the left and 2 nozzles on the right. Up top, we have rotors. Each one of these are multi-rotors. So they typically have between 6 and 8 rotors, although some models have fewer than that. And all the electronics are actually housed in this blue top up here. So that's what we're going to be talking about today, spray drones. And here are many different examples of spray drones that are available on the market today. And as I mentioned, there's quite a variety of drones out there, anywhere from 4 to 6 to 8 rotors, different payload capacities. For instance, this one on the bottom right-hand side down here, this holds 5 liters of spray. The one on the bottom left holds 10 liters of spray. The one up here, the top left, holds 16 liters of spray. And then the one over here on the top right holds 20 liters of spray. So there's a price difference, of course, as you might expect for each one of those, because the more payload that you're carrying, the bigger the motors have to be, and the props and everything else that goes into it. But you'll find a lot of similarities. They all have a hopper, as we talked about before. They have landing gear, although the landing gear are different configurations. This is different than this one down here on the left-hand side. But there's a lot of similarities between them. And then even in addition to the spray drones, we have drones that can carry granular materials. These can be used to put out fertilizers or seed or ant bait or something like that that's of a granular nature. So we have both spray and spreader type systems with these drones. What I'm going to talk about first is some of the technological challenges. And the first one right off the bat is payload. We talked about the payload of these being anywhere from 5 liters up to 20 liters, but you're really only talking about 4 or 5 gallons at a time that you're able to carry on these units versus the manned conventional applications where you may have 400, 600, 800, even up to 1,000 gallons of hopper capacity. So payload is one of those issues with these drones that we run into from a technology standpoint. Now, the other challenge that we have is battery life. These use LiPo batteries, lithium polymer batteries, but your runtime on these is typically only in the 10 to 12 minute range. So they have limited battery life that we have to deal with. And then it takes 30 to 45 minutes normally to charge these back up. So you have to have multiple sets of batteries to continue operation in the field. Then one of the other things that I've done a lot of work on is looking at patterns, spray patterns, and the effective swath of these units. For manned aviation, you might have anywhere from a 60 to say 80-foot swath or so for some of the manned aircraft. But for these, typically they're in the range of 10 to 30 feet. And it really depends on droplet size. So as you have finer droplets, those get pushed out by the rotor wash, which is pushing down. In order for the drone to stay up, it has to push air down. And so when you have a finer droplet spectrum, it's actually able to take those fine droplets and push them out and increase the swath. Of course, you're going to have resulting drift from that too, possibly. So it's best to kind of stay away from those fine nozzles as much as possible and go with either a medium or a coarse nozzle. But as you go to a coarser nozzle, it reduces your swath because those droplets go more straight down rather than being spread out. Application rate is another challenge that we run into. Many of the labels have a minimum application rate of 2 gallons per acre, but with the pumps that are on these systems and just the small capacity, you have to go fairly slow to get 5 gallon per acre application rate. 2 gallon per acre is fairly easy to achieve, but still you're limited on the productivity because of the way that the systems are set up and the pumps that are on there. Productivity is one of those other challenges that brings all these other factors together. And let me give you an example for that. So we know that the acres per minute that you can cover is the speed times your swath speed in miles per hour times your swath in feet divided by 495. So let's run an example real quick of what this might look like. So an average speed for a drone is about 6 miles an hour. We have a swath, let's say in the middle, about 20 feet or so. This is a medium droplet size. And then that gets us about 1/4 of an acre per minute that we can cover. Now, let's say we take that 1/4 acre per minute, and let's say that we have 10 minutes of battery life per set. So that means we can cover about 2.5 acres in 10 minutes. Now, it takes a little bit of time to come back, change out batteries, reload. Let's say that you have 2 minutes to do that. That means we have a 12-minute turnaround time for each load. So what that translates into is about 12 acres per hour. Okay, so that's realism right there for these smaller drones that are in that 50 to 75 pound range. Now here's a test that we did out in New Mexico a couple years ago for control of grasshoppers. This is a ULV application, so it's 7 formulation at 16 ounces per acre, so 8 ounces of carbaryl and 8 ounces of water per acre. And so for this one, I was actually able to put it on very quickly, running 20 miles an hour, 10 feet off the ground to get our application rate that we needed to. These were 10-acre plots that we're spraying. And for this, it worked really well when you have a low application rate like that. And, for the whole 10 acres, I was carrying about 1.5 gallons on board. So it's fairly light. The batteries lasted plenty long enough to do that whole 10 acres. And then what happened with this is we had really good control of the grasshoppers. The grasshoppers, there's not a whole lot of grass out there in the first place, but we were able to do the whole application, 10 acres, in about 5 minutes. So that's a really good application for spray drones. Now, there are some regulatory challenges as well. Any of the drone applications, just a drone operation has to fall under the FAA 14 CFR Part 107. So any drone pilot has to, for any kind of commercial purposes, has to have a Part 107 certificate. And what that means is they have to avoid manned aircraft, they have to yield the right of way, they have to operate in a responsible manner, they have to keep the drone within eyesight. It's called visual line of sight. So they have to be able to see it at all times. There's only, at this point, it's 1 pilot to 1 drone, unless you have a swarming exemption where you can operate more than 1 drone per pilot. You can't have operations over people, just bystanders, unless they're part of the operation. You can't have operations from a moving vehicle. It's only during daylight hours, unless you have a nighttime exemption. You have to have good weather visibility, 3 miles. You can't go above 400 feet AGL, above ground level altitude. Maximum speed is 100 miles an hour. It's usually not an issue. You have to stay below 55 pounds unless you have an exemption that allows you to go over 55 pounds as well. And this is all from the FAA. You can't fly within 5 miles of an airport unless you have special permission to do that as well. You must register each aircraft, and you must have a remote pilot certificate. That's that Part 107. That's for any commercial drone operation. Now, in addition to that, we have pesticide application license that you have to have if you're going to dispense any type of pesticide by air. And so that falls in an additional category called a Part 137 certification. And this is what all aerial applicators have to have, a Part 137. And these regulations govern agricultural aircraft, of which drones are an agricultural aircraft. It's just that the pilot is on the ground and not in the cockpit in the US, and it encompasses the dispensing of pesticides. So we have to abide by all these regulations for dispensing pesticides. Now, we also have to work with the EPA. The EPA is trying to figure out how drones, especially spray drones, fit in to aerial application, into the labels. So the chemical manufacturers are working with the EPA to ensure that current labels are appropriate for UAS aerial applications, and they're collecting data to see how that works and how much drift results from these types of units. And in Canada, they're interested also in efficacy and exposure of these pesticides by drone. So there are a lot of opportunities really for this new platform. One of those is invasive species, being able to control that in areas that are difficult to get to, or maybe just small areas where it wouldn't make much sense to hire a large manned agricultural aircraft to come in and spray. And then there may be in an orchard, you might not want to spray a 100-acre orchard with a drone, but what if you identified some hot spots within the orchard where only a dozen or so trees needed to be sprayed? Well, this is a perfect platform for being able to identify the locations of those trees and then using the drone to go and spot spray. There's other opportunities where it's very dangerous for manned aerial applicators to get into in a field. You may have power lines, tree lines, wind turbines, etc., that are just very dangerous on the manned side of things. Typically, the industry loses 8 to 10 pilots a year due to accidents from making these applications. And so if we can address the dangerous parts of the field with the spray drone, it just makes a lot of sense to do that. There's also difficult areas to access, such as this or this, where a spray drone could go in and take care of these problems. In addition, especially small farms or organic farms, where a lot of the work is done with a backpack sprayer, we can save a lot of the labor that's required right now to do that, and we can reduce human exposure to these chemicals. So even in vineyards here, we have an enclosed cab that's making these applications to a vineyard. So this is pretty good technology. Drones can do this as well. And then you have applications like this where you might not have an enclosed cab. And so your exposure of your operators becomes important to reduce that exposure. And then heaven forbid, we have a situation like this with backpack sprayers right out in the field. So drones can carry the heavy loads and do these types of applications. The pilot just stays on the upwind side of the application or the field, and then there's no exposure to the pilot. In addition to those opportunities is the ability for these drones to fly at night. They're autonomous, and so if you program the path of the field during the day and there's no obstructions, there's no reason why these drones can't fly at night and protect our pollinators, which will be foraging during the day, but going back to the hives at night. So it reduces exposure to the active spray to the pollinators. And then there's also opportunities for vector control with these units, again, getting out to wet, marshy, swampy areas and making either adulticides or larvicide applications for mosquito control. Now for spot spraying, this is another unique opportunity, is to use the drone to spray specific weeds within a field. So for this one in particular, it's Johnson grass escapes in a fallow field at the end of season. And you can see this drone here has one single nozzle. I'll show you this right here, hold on a sec. All right, so this has one single nozzle that is targeting Johnson grass escapes in a fallow field. And so this is a really good application for drones because they have limited payload. But if you can put on an ounce or maybe 2 ounces of product per weed, then that goes a long way. And you can, I found from our research, you can cover 50 or 60 weeds per battery set for this. And so I've been working with the weed science group at Texas A&M and their graduate students on some of these projects. And they do the weed identification using remote sensing. They take an image of the field and then they identify where those weeds are within the field. And then they create a shape file that I can then import into my spray drone. And I can go out and with an RTK GPS system, I can make these spray applications within 1 or 2 inches of where the plant is located. And so this is a really, really good application for spray drones. So that was back 1.5 years ago. And then this last year, it's been green on green spot spraying, where the first study we did was here in rice down in South Texas. And then we'd follow that up with a spot spray study in cotton, targeting Palmer amaranth. And interesting enough, the last study we did was on a golf course for control of Kalinga and turf. And so these studies, they're compiling the results right now, the PhD students, and are presenting those this month and next month at professional society meetings. But these are really good applications for a spray drone. So what does the future hold for spray drones? I think we're going to see higher payloads above that 55 pounds, maybe even above 100 pounds. So the capacities are going to get larger and larger. There's going to be larger aircraft to be able to carry those payloads. And then the other way to do that, instead of having one large aircraft that carries, say, 100 gallons or something like that, you can have a drone swarm. Now, you do have to get an exemption from the FAA to do this, but there are companies in the US that do have these exemptions to fly multiple drones at one time. And this allows you to cover more acreage, right? So if you have 4 or 5, 10 drones out in a field, you can cover the area that you need to quickly. Automatic swap offset is taking into consideration meteorological conditions in the fields, so that if you have a wind blowing towards a sensitive area, if you have a MET station, a weather station set up in the field, it can be programmed to communicate with the drone and tell the drone to move upwind to make that first spray application, so that the spray stays in the target field and doesn't drift downwind. There's precision application controllers that are going to be coming on board, not only to make variable rate applications, but to be able to put the material exactly where it needs to be put. For the individual weeds, we have to take wind into consideration there too, because if you have a wind blowing at 5 to 10 miles an hour, it can move that spray off target 2 to 3 feet, and we can't afford to have that when we're targeting a single weed. VTOL capabilities. This is vertical takeoff and landing capabilities. So these multi-rotors they just take off straight up. They're just like a helicopter basically with multiple rotors. But VTOL means that you can take off like a helicopter, but then it's more efficient to actually fly like an airplane. So they can convert over to a kind of a fixed wing configuration once they take off. And there's more flight efficiency involved in that. So I think we're going to see more of those in the future as well. And here are some of the larger payloads that we were talking about. Now, this is in research and development and the very early stages of commercialization, but Pica is putting out something called the Pelican that has a 75-gallon tank on board. It does need a little runway, 150 foot of runway. It could be a grass strip to take off and land, but it's a big airplane that has, it's just like a commercial ag aircraft, except it's just a little bit smaller. It's 38-foot wingspan, 20 feet long, can fly 90 miles an hour. It can go 70 miles, and it can cover about 10 times what the smaller drones can. Of course, with this configuration, you have all your eggs in one basket. So if something happens to this unit and it's down, well, you're kind of stuck until it gets repaired. If you have a swarm, maybe one of your drones needs some repair, but then you have 9 others that can continue to work. So there's 2 different philosophies when you're looking at spray drones, and one is the large one that can cover a lot of acreage all by itself, and the other is the swarms. So companies are taking both approaches, and we'll see what happens in the end. All right, so it looks like at 23. So I'm going to have to speed through this other one just a little bit, but I'm going to talk a little bit about a fungicide study that I did in rice in Louisiana this last summer. So myself, Chung-Hai Yang from USDA, Randy Price, LSU, Shane Zhou from the Beaumont Research Station, Rice Research Station, and then Bradley Reed was our aerial applicator that we worked with on this study. So rice sheath blight is a fungus that causes a lot of damage. It is a global pathogen, so it's not just here in the US, it's worldwide. And it infects plants in a circular pattern that's sometimes called a bird's nest. And it can cause significant yield losses up to 50%, and can reduce quality of the rice as well. Starts at the water line and works its way up, looks like this. And this is the bird's nest that it looks like in the field. It just lays it right down. It makes it hard to harvest. It can be harvested, but you have to go real slow, and it just chews up your productivity of the field. So I worked with an aerial applicator out of South Louisiana on this project, and we actually had 4 different treatments that we were looking at. 2 of them were conventional type of applications using an air tractor such as this. For this one, this is an Air Tractor 502. They used a standard type of nozzle for it, straight stream nozzle. This is a Davidon tri-set nozzle, straight stream configuration, so it's coming straight back. It's producing a little bit larger droplets to reduce drift. And when we look at the way that this was set up, this might not mean a whole lot to you, but the 061 orifice is kind of a smaller orifice. Had the angles, the deflection on the nozzle, so it has just a little bit of deflection to break it up just a tad bit. 70 psi, running 130 miles an hour. The important thing to see here is that our VMD, our medium droplet size, is 460 microns. So pretty good droplet size, but that is to reduce drift as well from these applications. And this ends up being classed as a coarse spray. So for the 502, we had two different configurations using that same setup. One is the using for a 2 gallon per acre application rate was one of our treatments, which is kind of the lowest label rate for many of these. We use that 0.061 orifice. We had 47 nozzles flying 130 miles an hour, and we had a target swath of 64 feet. The other setup was for a 6 gallon per acre application rate. So looking at application rate, in the end, we want to see, does the application rate affect efficacy, yield, and control of sheath blight? So that second conventional type setup is targeting a 6 gallon per acre application rate, and that forced us to go up on the orifice just a little bit to the next size orifice. And for this, we had 64 nozzles set up on the plane, still at 130 miles an hour. Now, the third treatment that we had is using an Eagle aircraft. Now, you don't see many of these because they're not as productive. They go slower. But in this particular case, this applicator wanted to do a really good job of reducing drift. He wanted to virtually eliminate any drift claims. And by going slower, it doesn't break up the droplets as much and reduces drift, actually, as a result of that. So for this one, he also used a straight stream nozzle. It's not an aerial nozzle. Matter of fact, it's a fertilizer nozzle that they use for banding fertilizers. It's a solid stream nozzle, so it's still straight back, solid stream nozzle, but it allows him to control his droplet spectrum. And when we set this up, it's also for a 2 gallon per acre application rate, and he has 85 nozzles on here, but he's running 95 miles an hour, so pretty slow. And based on some of the pattern testing and what he prefers to run, we're at 60 feet for the swath. This is some of the pattern testing that we did at his site. And then you can see the droplets from this, pretty large droplets. This is on the order of 500 plus microns. So this is going to result in much less drift from these applications. Now the question is though, can you get good control from this type of droplet spectrum? Okay, at that application rate, 2 gallons per acre. So we did pattern testing. Part of that is running a string. We did cards, water sensitive papers, but then we also ran a string, and then we mixed fluorescent dye into the spray tank, and that dye and water deposited on the string and gave us a pattern. So this is what the pattern analysis looks like. We run it through. This is a special system that Randy Price at LSU developed using a GoPro to analyze the string. It's field deployable, and it works really well. So the pattern from the test that we ran, this is what the pattern would look like. To you guys, it may look a little choppy, but for what we call Operation Safe Analysts, the ones, us guys that do this type of analysis, it actually looks really good. You're going to get natural variability in the spray pattern, but this is a good overall pattern from this application. Again, this is another look at it, and we can see on this right-hand side, if we have a target swath of 60 feet, our coefficient of variation is 13%. We're looking for anything below 15% is acceptable for getting us a good pattern. And you can see that the pattern here looks real good. We have 4 different passes right here that we're averaging, and the pattern looks good. Now this is using the water sensitive papers right here. We did pattern with the water sensitive papers as well. And there was something, maybe a sample blew off or something right in here, or got turned sideways. And so it shows a little bit of a depression there in the middle of the pattern, but we know from the string that it actually looks real good. What I want you to note from here is that our VMD on this with the cards is over 500 microns, 566 microns. And then also we have a relative span. That's how tight the span of droplets is, from the smallest droplets to the largest droplets, how tight that span is. And we're looking for something under 1. And so this is 0.83 for this one. So really nice. And then when we look at how the droplets are spread out over that pattern, this graph actually shows you how large the droplets are. So white is extremely coarse. So everything underneath this pattern right here, up to this point here, is extremely coarse. So these are very low drift droplets that are being put out. And again, the question is, how well do they control the disease, right? And then the blue that you see over on this left-hand side, as the droplets get smaller, they get pushed farther out. So we get coarse droplets out here to the left-hand side, and a few medium droplets out there as well. But that's the droplet distribution for this pattern. And then when we overlap this, say like a field simulation, we get this type of pattern right here, and we see that the swath is 67 feet is what it says at a 15% CV. So really good. And then part of this project was taking aerial imagery and looking at what the disease looked like before we made applications and then afterwards. So Dr. Chung-Hai Young with our project here in College Station is in charge of remote sensing and used a drone to do some of this aerial imagery. And this is what it looked like. And beyond that, you kind of lose sight of it. So that's the drone. And he has several different multispectral cameras on there to get imagery data for that. And he used reflectance charts as well to calibrate his images. When we first did the study at the end of June, there was just a lot of cloud cover. So it was really hard to get good aerial data at the beginning of the project. So we relied primarily on what happened right at the end before harvest. We also worked in collaboration with Dr. Shane Zoe out of Beaumont, Texas A&M AgriLife Research Station out of Beaumont, Texas. He's a rice plant pathologist. He and his team went out before our applications and then 6 weeks after our applications and did efficacy evaluations. They did health assessments of the rice plants and the disease, the severity of it before and then after application. And see, the product mix that we used for the applications had Artisan, Trevup, Verifact, Penetrator Plus, and Control. It was a mixture of fungicides and adjuvants as well for the spray mix. And then this is what it looked like for the conventional applications. All right, and then Bradley came in afterwards with his Eagle and made the other application with 2 gallons per acre. All right, so those are the applications. And then within the field, we had 10 by 10 tarps within each of the areas that we use for control, like an untreated control. And then at the end of the season before harvest, this is what it looked like. And you can see in this area, especially up on this end of the field, there's a lot of that bird's nesting, which is an indication of the disease. And then right along this edge, quite a bit. And it probably has to do with the way that, from the predominant wind direction and water flow up against those levees as to where the disease kind of accumulated. And then some of the aerial imagery that Dr. Young provided for this at the end of the season allowed us to quantify what that disease looked like. And it really, he said it was highly correlated with the red areas here in this photo. And so you can see on the right-hand side, you can see how I had the treatment randomized within each of these blocks. So this is rep 4 up top here, and then we had rep 3, all the treatments randomized within that, and then rep 2, and then rep 1. And what we found, what Dr. Zhou found from the initial assessments is that in rep 1, there wasn't enough disease for them to even detect. So down here on the bottom, we ended up just leaving rep 1 out when they were doing this assessment early before the applications. They didn't find any disease. So we ended up leaving rep 1 out, and we used rep 2, 3, and 4 for the assessment. And here are the results. When we looked at the infected area based on the aerial imagery, and this is percent of the area that was infected before harvest, the air tractor, the conventional application with the 2 gallon per acre rate, had the most area that was infected with the disease. And then next to that was the air tractor at the 5 gallon or 6 gallon per acre rate, and that was a little above 15%. And then the Eagle aircraft at the low application rate, 2 gallons per acre, was just right at 14%. So Dr. Zhou went out and did the disease assessment both at the beginning and also after, at the end of the season, right before harvest. And this is what that disease looks like. It's these black spots, smut, that comes from these kernels that get infected right here, and then it drops that smut down onto the leaves. And from his assessment, looking at the increase in the disease from early season to 6 weeks later, this is what he found, is that the air tractor, the 2 gallons per acre, had about 125% increase in the disease. The air tractor with the 5 gallon per acre application rate ended up with about 135% increase in the disease. The Eagle with the 2 gallon per acre had 100% increase. So nothing was completely effective in controlling and stopping the disease. But then the untreated control, we had about 155% increase. So these, the Eagle again, at that low application rate, ended up being the best treatment for us. And then the last part of this, and I won't dwell on this, but we did yield assessments. I worked with the farmer, taking yield from each of these plots, and then we put it in a weigh wagon, weighed it up, and then I knew exactly the area that we covered for getting that yield. And in the end, again, the Eagle with the 2 gallon per acre application rate had the highest yield of all the treatments at close to 6,900 pounds per acre compared to the air tractor conventional application with 2 and 5 gallons per acre. So conclusions with this is that aerial fungicide applications with an extremely coarse droplet spectrum applied 20 to 30 feet above the ground with the Eagle aircraft at 90 knots produced the following: as good or better control of rice sheath blight than conventional aerial methods, as good or better yields of commercial field rice infected with sheath blight compared to conventional aerial methods. And in addition, the 2 gallon per acre aerial applications overall provided as good or better control of rice sheath blight and yield than the 5 gallon per acre aerial applications. Now, this is 1 year of data, and additional research is going to be needed to confirm these initial findings, but we plan to follow that up with another study this year. So that wraps it up for me. And Tom, at this point, I'll turn it over to you, and you guys will have a chance to ask us questions at the very end. Thank you very much.
Okay, thank you. All right. Okay, everyone. My name is Tom Wolf. I'm coming to you from Saskatoon this morning. Thank you for joining us. We'll finish off today's webinar by talking about what's happening on the ground spray side of things. And I'm really eager to show you what's been going on. We basically have, in the last 20 years, have watched the sprayer become the most used piece of farm equipment on the farm. And the issues surrounding its performance are much more related to logistics nowadays than they are to actually the droplet size. And although we've always worked with droplet size in this field of work, we certainly, for example, I started my career with fine sprays trying to cut rates in the late 80s, early 90s. But we've found, drift control became important, and we used air induction tips. And ultimately, when we used some of the newer products that had issues with spray drift, such as dicamba recently, we've moved to even coarser sprays. But these droplet size issues have tended to work themselves out. We didn't feel it was necessary to deploy a research program particularly, but rather we were trying to help farmers achieve their agronomic objectives. And those, as I said, have to do with logistics. When you look at logistics, we can monitor the time spent that a sprayer spends in different modes. So for example, in this example, there were 8 John Deere R4045s tested, and these were large farms, about 5,000 acre farms, doing about 450 engine hours per year on average. In looking at the data, we noticed that about 30% of the time that sprayer is idle, almost a quarter of the time it's in transport, and less than half the time it's actually spraying. And the issue with the spray is really the fact that it has or the idle time rather, is that it has, I'm just sorry, I have to get rid of my screenshot here. my little thing here's gone. Okay. Is that most of the time is spent doing tasks that are unrelated to spraying, cleaning, and filling. So we started to become very involved in looking at the other side of the sprayer that is used to fill and clean. And we see a number of different components there that are often very interesting. Water tank, pump. Would you believe that one of the most productive elements on a modern spray outfit is actually the transfer pump? How many gallons can you transfer per minute? How long does it take to fill that sprayer? And what are the logistical aids that you have? How fast can you induct your chemical? Can you do it in 3 minutes, or does it take 15 minutes? Those are very, very important components of the spray operation. And so we spend a lot of time actually helping producers figure out how much time they actually spend spraying. And we like sprayers that feature some of the logistical components in their original design. Some, for example, some European sprayers that are coming to North America have some of those nice features. I want to just highlight a couple for you before we go into what's happening on spot sprays. One of them is continuous rinsing. When we have a traditional sprayer tank that is running empty, we typically spend a lot of time rinsing that sprayer. But by installing a second pump that is dedicated to a clean water tank, and this is not featured on most modern sprayers, this is an aftermarket install, we can clean the water tank while we're still emptying out the last bit in the sump. So we're basically logarithmically diluting the remainder in the sump, cleaning the plumbing, the recirculated plumbing, while we maybe finish off on the headlands and emitting the last remainder. By the time that clean water tank is empty, the tank is essentially reasonably clean. The plumbing is reasonably close to water, and we can now pursue maybe screen cleanings and so on and so forth. We've identified ways people can do this and are publishing those on our website. So essentially what we found is one of the limiting factors to productivity is something very simple, like knowing how much liquid is in your tank. So we are happy to report, there's some solutions to this. This happens to be a little load cell that measures the weight of liquid. A farmer can install this in line with their sump and very quickly understand how much liquid is left in the tank so that they can more accurately meter out how much is left and how much needs to be disposed of, and thereby minimizing time and waste. And they get a readout in the cab that's to the nearest gallon of actual product, any slope position of that particular tank. This is a much better way of measuring liquid volume than by looking at a sight gauge or even counting it down with a flow meter, which may have inherent inaccuracies. So if we look again now at farmers that typically use a traditional way of idling, transporting, spraying, and are maybe doing 86 acres per engine hour, the people that are using something as simple as a fast fill are able to essentially produce a 50% increase in their performance just by implementing maybe attention to the tendering process. So not anything to sneeze at by any means. A quick comment about deposition uniformity. Dan showed some great slides of his patternation work with aircraft. We are very concerned that similar kinds of situations are happening with ground sprayers. Are not as clean aerodynamically as we once thought. They're not traveling up to 20 miles per hour, for example. So that does create some turbulence. It creates some displacement of small droplets. And when we've measured this on string, similar to Dan's method he showed, we use a monofilament line, but the overall deposition uniformity of those sprayers is actually not as good as we thought it was. And the tractor unit right directly, where the boom is directly behind larger wheels, has a significant signature on this. Now, this is a high and fast boom with a side wind. When we slowed the sprayer down and went to a lower boom, we were able to improve that coefficient of variation significantly. We still have some issues, but again, the point is, if we want to do a better job spraying, we may have to slow down the operational speed. If we slow down the operational speed, we lose productivity. How do we gain that back? Of course, it's again logistics. The last part of the presentation today is going to be about philosophy. And it's really about the ongoing emergence and growth of resistance. And I put a picture in there of Palmer amaranth, the baddest weed of them all. It's actual potential geographic range is all of the growing area of North America. And let me just ask you to ask yourself a question. Does anybody think that the Palmer amaranth problem will go away, or that less area will be affected by Palmer amaranth in the future? Or is the opposite of that true? And the old adage that we're okay as long as our management stays ahead of resistance, is that applicable? And I want to show you some slides that you may have already seen. And this is basically from Ian Heap, who runs wheatscience.org. This is the sort of the trend line of herbicide resistant cases globally. This arrow here is 1982. So it happened post 82 for the most part. This is the history of the development of herbicide modes of action. And this is 1982. And you can see that most of our herbicide development happened before that date. These are the herbicides that are effective against Palmer amaranth. And these are the ones that are effective against resistant Palmer amaranth. So I've removed all the modes of action to which Palmer amaranth has been shown to, and in published literature, to show a resistance, not all in one plant, but it's possible genetically speaking. So that leaves Reglo and paraquat, a desiccant, or a broadleaf herbicide in soybeans, for example. So not a lot of options left. And what are we going to do about that? And the real question is, of course, we can't spray our way out of resistance. That's an old adage that many people use, and it's quite accurate. But we can possibly prolong the utility of our herbicides by using optical spot sprays. So Dan has already alluded to that. Essentially what this means is we have a sensor. The sensor is able to detect the presence of a weed, and it can activate a nozzle. And these sensors can be mounted on the boom, and they can be mounted on drones. This happens to be the Trimble Weed Seeker. This is the Romatron Weed It Croplins that distributes that in Canada and Australia. And it basically identifies small plants on a brown background and sprays them. Uses a light that senses chlorophyll, and is actually, a bit fun to watch. I hope that this video will translate. I know it's a little choppy at times, but what you can hopefully see here is that the nozzles are individually pulsing as they sense. So this kind of a system can operate day or night, and can in fact detect weeds accurately down to a dime size, and at up to 15 miles per hour. John Deere has entered this realm. They have announced John Deere See and Spray Select, and it uses an RGB camera, not a chlorophyll detector. So it just basically says, is this green? And if it's green, it assumes it's a plant, and therefore it sprays it. And of course, we can now, with integrating into our monitors, basically develop a weed map, a very accurate weed map. Others are following suit. This is Bilberry. This is a green on brown application, but Bilberry actually also uses their system on green, and we'll just talk about that very quickly at the very end. This is the open weed locator developed by Guy Coleman, who is a PhD student at the University of Sydney in Australia, who's currently studying in Texas, I believe. And he has published a way to build your own spot sprayer with algorithms and hardware requirements. And if you can solder and have some time, maybe that could be a fun project. Other ways of using these sensors are also very exciting. I know I'm speaking to agronomists today, but in Western Australia, they've used a weeded sensor to make a spot cultivator. So basically, if you want to minimize cultivation, you can do that just by activating the hoe on individual plant that's sensed. So a very, very cool development. But the real revolution we're all sort of waiting for to some degree is machine learning. It's here. And with machine learning, we can speciate plants and possibly make decisions on the go. This happens to be a drone map, but you can see that with a grid pattern, they were able to develop a heat map of their patchiness of their weeds. And then ultimately, they were able to go to a field view, look at just the Amaranthus species, find the heat there, and then essentially scroll down to a field view of that site and basically identify what the drone saw and what it's been labeled as. So it's very, very exciting. The same technology is now on booms, on boom cameras, able to do this in essentially just a few milliseconds and make a spray decision based on not only if it's a plant, but also what kind of plant it is. This is Bilberry, who I mentioned already. This happens to be an Australian deployment of their wild radish algorithm. You can see that it's detected wild radish, looks like wild mustard, in a canola crop in Western Australia, which is quite a feat. And they actually are selling this commercially, a green-on-green sprayer on the AgriFac, made by Bilberry, and you can buy the wild radish algorithm for about $350 per acre. But you don't have to use herbicides. You can use other products that are possible. This happens to be a laser. We're really just talking about whether you can detect things and then choose your control method, and herbicides may not be the answer. The space is actually getting pretty crowded. I just want to finish off by showing you who the main contenders are currently. So as we know, John Deere bought Blue River. They were probably one of the first to do this, but they've been fairly tight-lipped since being purchased by John Deere. Bilberry, I mentioned, they're French. Carbon B works with Kuhn, a French sprayer manufacturer. Exact Robotics, a startup, but funded and owned by the Excel Group that makes a large number of sprayers in Europe. They have 30 PhDs doing machine learning right now. Green Eye is a company that's announced entry into the US market in 2022, green on green. Precision AI is doing it by drones right here in Saskatchewan. They're doing green on green as well. Tyrannus is a drone deploy kind of idea. They'll give you the maps. Zarvio, we've all heard of Zarvio, BSF, Bosch. There's a German venture, but a very international in many ways. So lots of space, lots of excitement. I think, in summary, the three takeaway messages I'd really like to share with you is spraying is increasingly about logistics. The droplet size issues we can solve. Resistance growth continues. And the reason I think that sensors and optical spot spraying hold promise is that they prolong the utility of herbicides essentially by allowing us to use multiple effective modes of action. I just want to thank the American Society of Agronomy for the opportunity. I want to remind you we have a free website. It's paid for by the Grain Commissions. It's no advertising on it, that we publish our results on, our thoughts. They're meant for practitioners. So thanks very much. Chris, I'll turn it back over to you.
All right, thanks, Tom. Also, thank you, Dan, for the presentation as well. We do have some time now for questions. We do have quite the list coming in, so I appreciate that. So the first thing I'm going to do, while we still have everybody here listening, Tom, Dan, would you be able to share any other contact information with these folks? Because I don't think we're going to get through all the material today. They may want to follow up with you individually. Dan, you first. An email possibly?
Yeah, absolutely. So it's just my name, dan.martin@usda.gov.
Perfect. Thank you, Dan. How about you, Tom? What would you suggest for contact information?
Go to sprayers101.com and click on my name, and it'll send an email to me or tweet me.
Perfect. That works. All right. Thanks to both of you. And so everyone, please take note of that. And if we don't get to your question today, which I suspect we will not because the list I have, please reach out to them individually. So, all right, here we go. Dan, to your presentation, this individual asks, are drones ideally better suited for agronomic crops or horticultural crops or permanent crops? What's really the ideal application? Maybe now, maybe in the future.
Well, I think there's good applications all the way around. I have a presentation here in about a week or so to the Watermelon Growers Association. So I think it's a platform. It's just another platform for spray application that offers many advantages. And one of the advantages is that it can fit in tight areas. There are certain, as I mentioned a little earlier, there's small farms, a lot of small farmers, organic farms that may only be 5 to 10 acres. It just doesn't pay to bring a large commercial ag aircraft in to spray those types of areas. And if we can reduce human exposure by replacing backpack sprayers, all the better, right? And so I think there's lots of applications for it, especially on the small farms, except for the larger platforms that are on their way, like the Picas of the world. And there's, I think, a large multi-rotor that's soon to be released. So there's going to be some larger platforms available here pretty soon for broad acre. But right now, it's smaller farms and spot spraying are the unique niches in the industry.
All right. Thanks, Dan. Next question. Actually, I have quite a few questions coming in about cost of various things here. And I'm going to direct this to both of you. How does the cost compare of a typical application from the traditional ground-based unit to the traditional aerial, let's say plane-based unit, to drone spraying, on a per acre basis? Can you answer that? I know it's a little bit broad. We're not talking about, I'm not even outlining a crop here or a product or anything. But how about some cost estimates in a comparison?
Maybe I'll start just with the ground. I only have ground numbers. The cost per acre of running a modern ground sprayer is somewhere between $10 and $15 per acre, 8 to 12. It depends on where you are, but that's kind of the fixed cost, labor, depreciation, fuel.
Yeah, so Chris, on the aerial side of things, excuse me, I really haven't done the cost per acre per se. I know that the drone costs for the lower capacities range anywhere from about 10,000 up to about 50,000 for some of the units with the larger capacities. As I mentioned, they're running on the order about 12 acres an hour. So you could probably run the numbers on that and see, where that plays out. But it's an emerging technology, and as the volume increases of the number of units produced, that price will come down.
And I would say, based on the numbers you just shared with us, Dan, that drone spraying is incredibly competitive. I mean, we're talking about an investment of maybe 20,000. Sprayers on the ground are costing 500,000.
And the same for conventional manned application as well. Those are $1 million aircraft, right? So, yeah.
Good point. Thank you. Thank you both for contributing to that answer. Dan, I'm going to direct this to you. We have a question here. It's pretty practical. Concerning pesticide label interpretation with respect to applications made with small UAVs, would the pesticide need to be approved for aerial application?
Yes, that's my understanding. Is it has to have an aerial label for it, but many products do. At this point in time, the EPA is letting drone application fall under the aerial label. So there's normally a ground label and there's an aerial label. If it's labeled for aerial, at this point in time, it can be used with a drone spray.
A different situation in Canada, we have our federal regulator has differentiated those two application methods, and they are saying you cannot spray by drone unless you have a drone label. We currently do not have any drone label, so there's no commercial legal use of drone spraying currently in Canada.
Yeah, Canada is different, so it's good to note that is different. PMRA has different standards for drone sprays than the US, and I think no pesticides can be applied by drone right now currently in Canada.
That's correct.
Okay, very good. Just got a little bit of time left here before we shut it down. Interesting question here, and it goes towards the education side. Is there a website that simplifies and or shows the proper steps to get certified to be able to spray with a drone? Is it Sprayers 101? Is it a different website? Tom, Dan, what do you suggest?
It's not Sprayers 101. Dan?
Hey, Chris, so some of the UAV manufacturers have tried to simplify that process. A couple of the big ones that I will mention is Leading Edge, Aerial Technologies, and HSE-UAV, hse-uav.com. Those are just a couple of them, but it seems like the UAV manufacturers are kind of taking the lead on trying to make it a little more understandable, the process of getting those certifications that are necessary. But you do want to make sure that you go through the proper steps to make sure that everybody's safe and that the products are applied as they should be. So please take time to go through those. I went briefly through some of the regulations that are currently in place, but there is a process there, and expect for it to take some time. It just does.
Okay, thank you, Dan. Well, thanks to both of you. Certainly, folks, check out Sprayers 101 if you want to learn more about the topics presented today and other aspects of spraying. And with that, we're going to wrap it up. Thank you, Tom. Thank you, Dan. We appreciate you both being with us today. Thank you, Crop Protection Network, for generously sponsoring this webinar, and again, the larger webinar series that this is part of. So please come back for the remaining webinars in this series. And with that, folks, be on the lookout for a copy of the slides and a recording of today's webinar. With that, I wish you all a great day and a great week. Take care. Bye-bye.
Thanks, Chris.
Thank you.